Right now, the ground under your feet is moving. Not shaking, moving. About as fast as your fingernails grow. You'll never feel it until one day, without warning, centuries of built-up motion release all at once, and the Earth itself breaks. That's an earthquake. And by the end of this video, you'll understand exactly why the solid ground you stand on is one of the biggest illusions on the planet. Start with this. Earth is not one solid shell. Peel back the surface and you find the crust, a thin, brittle layer, only about 20 kilometers thick under continents. That might sound like a lot, but compared to the size of the entire planet, it's thinner than the skin on an apple. Below that crust sits the mantle, thousands of kilometers of hot rock, so hot it behaves like an extremely slow-moving fluid. It doesn't melt into liquid magma everywhere, but it flows over millions of years, the way thick honey flows over minutes. That slow convection, heat rising and sinking inside the mantle, is the engine for almost everything that happens above it. And the crust doesn't float on that engine as one piece. It's cracked into roughly a dozen major slabs called tectonic plates, plus a number of smaller ones. Some carry continents. Some are just ocean floor. All of them are moving all the time in different directions, at speeds of just a few centimeters a year. Here's the part most people get wrong. Earthquakes don't happen because the Earth is unstable. They happen at very specific locations along faults, which are basically cracks in the crust where two blocks of rock are trying to move past each other. Most of these faults sit right at the edges of tectonic plates, where one plate meets another. Depending on how the two plates are interacting, you get different kinds of boundaries. Some plates are pulling apart, stretching the crust until it fractures. Some are colliding head-on, crumpling into mountain ranges or forcing one plate to dive beneath the other. And some are just sliding past each other sideways, grinding like two ships passing far too close. That sideways sliding type is called a strike-slip fault, and the most famous example on the planet sits in California, the San Andreas Fault, where the Pacific plate is slowly grinding northwest against the North American plate. Now here's the mechanism, the actual answer to why. Two blocks of rock, sitting on either side of a fault, are being pushed by the slow motion of their tectonic plates. But rock isn't smooth. It's rough, and it's under enormous pressure, so friction locks the two sides together. They get stuck, but the plates don't stop moving just because the fault is stuck. The rock on either side keeps bending, keeps stretching, storing up energy like a twisted rubber band. For years, decades, sometimes centuries. Geologists call this elastic strain. The rock is deforming, but it hasn't broken yet. Eventually, the stress building inside that rock becomes greater than the friction holding the fault together. And when that threshold is crossed, the fault doesn't slip a little. It slips all at once. Years, sometimes centuries, of stored motion release in a matter of seconds. That sudden slip is the earthquake. The energy that was locked into bent, strained rock converts instantly into violent shaking, heat, and sound. That's genuinely it. No mystery, no myth. A slow-motion tug-of-war, followed by a sudden break, so the fault breaks deep underground. How does that turn into your coffee cup rattling on the table? The point where the rupture actually starts, underground, is called the hypocenter. The point directly above it, on the surface, is the epicenter. That's the location you usually hear reported after a quake. From that rupture point, energy radiates outward in seismic waves, and there are a few different kinds. P waves, primary waves, arrive first. They compress and stretch the ground as they travel, similar to a sound wave, and they move fast. Then come S waves, secondary waves, which move the ground side to side, arrive a little later, and tend to cause more damage. Finally, surface waves roll along the top of the crust, similar to ripples on water, and they're usually responsible for the most destructive shaking in a strong quake, because they linger longest. The deeper the rupture happens, the more rock the waves have to pass through before reaching you, which is part of why shallow earthquakes, closer to the surface, tend to cause more damage than deep ones of the same size. So how do we compare a small tremor to a catastrophic quake with magnitude? You've probably heard of the Richter scale. What's less well known is that modern scientists mostly use an updated version called moment magnitude because the original Richter scale becomes unreliable for very large earthquakes. Moment magnitude is based on the physical size of the rupture, how much the fault slipped, and how large an area broke converted into a single number. Here's the part that surprises people. The scale is logarithmic, not linear. Each whole number increase means the shaking amplitude is about 10 times larger, and the actual energy release jumps by roughly 32 times. That means a magnitude 7 earthquake doesn't release twice the energy of a magnitude 6. It releases over 30 times more. A magnitude 8 releases around 1,000 times more energy than a magnitude 6. That single-digit number you see in a headline is hiding an enormous difference in destructive power. Here's a number that might change how you think about this planet. Modern monitoring networks detect around 20,000 earthquakes every single year. That's roughly 55 a day. Almost none of them are felt by anyone. Most are so small only sensitive instruments can pick them up. But on average, based on over a century of records, the planet also produces about 15 major earthquakes of magnitude 7 in a typical year, and one earthquake of magnitude 8 or greater every single year, somewhere on Earth. This isn't a rare planetary event. It's a constant, ongoing process, and it has been happening for as long as Earth has had a solid crust, and there's a hard limit on how big it can get. No known fault on the planet is long enough to produce a magnitude 10 earthquake because magnitude scales with the length of the rupture. The longer the fault that breaks, the bigger the number. So there's a ceiling. It's a massive one, but it's there. This also explains why some places live with constant earthquake risk, while others almost never feel one. Most of the world's seismic activity and its volcanic activity traces the edges of the Pacific Plate in a horseshoe-shaped zone nicknamed the Ring of Fire, running from the western coasts of the Americas, up through Alaska, down through Japan, the Philippines, and into the South Pacific. If you live near a plate boundary, earthquakes aren't a freak occurrence. They're a structural feature of where you live. If you live deep in the interior of a continental plate, far from any boundary, major earthquakes are rare, though never technically impossible. One more piece worth knowing: earthquakes rarely travel alone. After a major rupture, the surrounding rock has to redistribute the stress that just shifted, which is why aftershocks follow, sometimes for days, sometimes for months. And occasionally, smaller tremors happen before the main event called foreshocks, though scientists still can't reliably tell a foreshock apart from an ordinary small earthquake until after the bigger one has already happened. That's also why, despite decades of research, no scientist, not the USGS, not any seismologist anywhere, can currently predict exactly when or where the next major earthquake will strike. What they can do is calculate long-term probabilities for specific regions, which is a very different thing from a prediction, but it's the best tool we currently have.